topic is getting what you paid for. And surprisingly, a lot of places are less concerned about that than they probably ought to be. Whoop, let's see, let me get control of that. And there's a whole art and science of ensuring that you get what you paid for, and that you deliver to your customers what they paid for and what they expect. And a lot of times that falls under the title of supply chain management, and you'll have a title like a supplier quality engineer or a supply chain manager. And what we're going to talk about today is some of the tools and some of the strategies that you can use to make sure that you get what you ordered and what you paid for. Because what you'd like to be able to do is just take stuff that your suppliers send you and take it right off the dock and put it into stock and have a dock to stock program. So what we're going to talk about is some of the various strategies that are employed, some of them not very good, and then we'll give you a recipe that you can follow, and basically a set of documents that you can require of your suppliers. And if they comply with what we're about to tell you, then you can, with as much surety as you can get, you can take the stuff straight from the dock and put it into stock. I don't know, does ATK do that? Do you have a dock to stock program?
We do in some very small classifications of materials, and we'd like to do just what you said. We'd like to move toward it in a bigger way, with confidence in what we have and the acceptability of what we have.
Yeah, it's a big issue. If you can have confidence, if your suppliers do their job and don't miss, it sure makes your life a lot easier, doesn't it?
That is the goal.
Yeah, okay, well, I'll help you. Okay, so here's strategy number one. Take their word for it. Just accept whatever they send you and assume that it's good. After all, they're the experts. How well does that work out, Warren?
Next page, please.
Yeah. This is up here kind of as the talking point. And the point of the slide is that that's a crummy strategy. You know.
Yeah, we agree.
You have to have a way of making sure that things are good. And the second strategy is that you 100% inspect every feature of every item. How's that going to work out? How's that going to work out, Fred?
Expensive.
Yeah, yeah. It's also surprisingly ineffective. There's a joke in the quality business that 100% inspection is 80% effective.
Mm.
And that's really kind of optimistic. Okay? It's like the old joke about Murphy was an optimist. In fact, I've got a little thing that I'm going to do for you here. The next slide that I put up, Fred will laugh because he's seen this before, but do participate. And Lestel, you as well, if you please. We don't have a lot of people here. I'm going to put up a slide, and what I want you to do, we're going to inspect some text for the sixth letter of the alphabet. That's the item that we're trying to detect. So figure out in your mind what the sixth letter of the alphabet is. And here in just a moment, I'll go ahead and get you started. And your deliverable is to tell me how many times the sixth letter of the alphabet occurs, and that's an inspection exercise. And so we'll see how we do. Is everybody ready?
Yep.
Ready.
Oh, okay, here we go. That's 30 seconds. Ten more. Okay, how many did we get? Warren?
29.
29. And is it, wait, I'm sorry, is it Janine or Jean?
Jean.
Jean, how many?
I did not complete my task, but I got 32.
You did well. Lestelle, did you count?
I counted. I didn't complete it, but I got 31.
Okay, and Fred?
I was also unable to complete, but I was at 35.
35. Wait a minute, I've got, see, I didn't count because I know the answer. 29, 32, 31, 35. What's wrong with this story, Gene? Where have we gotten off the rails here? How come we didn't all get the same thing?
A lot of variation in the process. For
yeah,
sure.
yeah. 100% inspection is not very effective. A long time ago, I worked at iOmega, and the guy that's currently my business partner came walking by my office area, and I said, "Hey, Wayne, you look pretty glum. What's the matter?" And he says, you know, we got a shipment back from Dell Computers, and we've got 100. We didn't meet our quality standard. We have to 100% inspect it." And I said, "Ooh, what's the quality standard?" He says, "Well, we can't have more than 0.5%. And I said, "You've got a problem then, because handling them again to inspect them will introduce 0.5%. And he says, "Yeah, I know." Just 100% inspection is just not very effective. And as Fred said, it's extremely expensive. Okay, so strategy number 3. This is
You didn't tell us the right answer, Denton.
I never have. Actually, Fred, in the years that we've been using that slide for about 5 years. Nobody has ever gotten the correct answer.
Which is?
He's going to ensure that no one ever does, right?
The guy that one guy did surprisingly well. It really amazed me what he did. He was done early. He just took a random sample of lines and counted those lines and made sure that he got them right, and then scaled it up by the size of his sample and got a very good answer. But
well, I got a very good answer. It just wasn't right.
Well, Fred, if you had gotten the right answer, you would have spoiled my example.
Okay.
Lot acceptance testing. Who can tell me about lot acceptance testing? Who's had experience with that? I bet Warren has.
I think Gene's the best to answer it, but I think we all have.
Gene, do you just love lot acceptance testing?
I'm not a huge fan, but sometimes it's the best we've got.
Yeah, the government insists on it. Warren, you had a comment. Go ahead.
I don't have a comment.
Oh, okay. As Fred knows very well, I got called in on an issue at the Lake City Army Ammunition Plant, and they were using lot acceptance testing. And of course, lot acceptance testing is where you draw a sample out of the shipment, a random sample, and then you have criteria, and the criteria that they had was they would draw 81 cartridges out of the shipment, and there could be no more than 3 defective out of the shipment. And there were some kind of tense relationships back and forth between ATK and the Army at that moment. Somebody got the bright idea, okay, we'll fix this. Instead of allowing 3 defective cartridges, we're going to set it at 0. That'll fix the problem. And so I said, just do a little thought experiment with me here for just a minute, because the math on this example was easy to do. So I said, suppose that we knew that absolutely all of our cartridges were perfect, but there was a saboteur in our midst, and in each lot of 81, or no, in each lot of ammunition that was shipped, he was placing a defective cartridge. And I worked through the math and said, okay, no, it was each sample lot. It was each sample lot of 81. He was placing a defective cartridge. No, that wasn't right either. Oh dear, now I'm confused. But the net result of the lot acceptance testing was that in whatever it was that I made up, the Army would end up rejecting 1/3 of the lots. Every lot had 1 defective cartridge, and they would reject 1/3 of them, and every lot that they accepted and every lot that they rejected would have the same 1 defective cartridge in it. Lot acceptance testing, the math just kills you. And hence the story that it works well when quality is poor. So if you've got a 5% defective rate, lot acceptance testing is for you. But if you get your quality down around 1% defective, it just stops almost stops working. And when your quality is excellent, it doesn't work at all. Fred will be the first to tell you that 99% quality is very marginal quality, very poor. And yet that's kind of the borderline where lot acceptance testing just flat lays down and quits working. The math just kills you because of the type of data that you're taking and the size of samples that you can afford. Forget it. Lot acceptance testing just doesn't work.
It's especially poor if you have to do destructive testing.
Yeah. Which firing a cartridge is.
Yep.
It's just poor. So we don't have a lot of sympathy with lot acceptance testing. It's just not a very good system. So that leads us to suggest strategy number 4. And this is a subset of the Six Sigma tools. We do most of our practice is Six Sigma, but we get hailed in every once in a while and do this subset for people to help them manage their supply chain. And basically, if you're looking for a set of documents from your supplier to assure you that you can go dock to stock, then this is the list of tests and the list of documents that has to be performed. And the number one thing is validate that you can believe your measurement system. If you can't believe your measurement system, nothing else matters. The next thing is test the creation process for stability and repeatability. Because what you really want is the supplier or yourself as a supplier to be able to do the same thing tomorrow as you did today. If you can't do that, your yield can go to 0 and you have no idea why. So
then is that basically gathering SPC on the critical data?
That is correct. And in fact, I'll expand on that in a minute. But that is absolutely correct. It's statistical process control, and usually that's going to be in the form of an INMR chart. Now, one of the reasons we recommend that is that INMR charts are about bulletproof. People tend to do them right. If you go to something fancier like X bar and R, our experience is there are more people that do X bar and R charts wrong than do them right. I don't know, Fred, have you had any experience with that indicates a preference?
The INMR, but it's been a long time, and we're just starting back into that world in ATK.
Okay.
The XBAR tends to group and hide variability too, so I don't like it very much.
Yeah, if you do it wrong, that's exactly what it does. If you do it wrong, that is exactly what it does. It will completely mislead you. If you do it right, it's actually a little more, it's more sensitive than the INMR. We can talk about that in a minute if you want. Once you've established that your process is stable and predictable, that is, that you can say, okay, I can do the same thing tomorrow as I did today, then the next thing we do is we test for process capability, and that's where you get into PPK and CPK and those kinds of constants or indices. And the last...
I just have a quick question to make sure that the nomenclature we're using were all calibrated. The creation process. Could you elaborate a little bit on how you're bounding that? What you mean by that?
Oh, that's whatever's making the stuff that we're getting or sending out. That's the work process. That's making stuff.
Okay. Thank you.
Is that a suitable answer? Did you get your question answered?
Yes, I've not seen it as creation process before.
Yeah, when I was making up these slides, I said, well, how am I going to describe that? And I made it up last night.
Oh, good. It might stick.
Who knows? And finally, you have to have a control plan in place to ensure that the key process variables stay put. So if you're asking for a package of data from your supplier to assure you that you can go dock to stock, this is what you want to see. Now, if you get the Auto Industry Advisory Group, AIAG, if you get their book on the production part acceptance process, they've got a little more detailed process, and it's a great process. That's a book that everybody that's dealing with supply chains ought to have on their desk. And what I'm going to show you is the heart and soul of the tools that's used. Okay. All right. Any questions so far? If this is the one thing that you, well, there are two things. Number one, lot acceptance testing doesn't work, and number two, these are the four things that we need in order to be assured that the process is going to work. Okay. So if you're trying to do dock to stock, we have some answers for you. And so I made up a bunch of lovely data here. Now, this is our QuikSigma software that we use in Six Sigma, and you really can just simply dive in and use it as is for the for your supply chain management. And if you want, you can even rearrange this navigator here and use it that way. But the first thing is measurement systems analysis, MSA. We maybe shouldn't use acronyms on our navigation because not everybody knows what MSA is. But it stands for, we're going to check out our measurement system. Warren, do you do a lot of that at ATK? Do you require that of your suppliers? Do you do it for yourself?
Not contractually, not that I'm aware of.
Okay. It's a good thing to know about, because if your measurement system isn't working, this whole system collapses, and it's so easy. It's so easy to do. And I'm just going.
Well,
go ahead.
Are you're talking about how we impose requirements for the acceptance of their parts.
Mm-hmm.
I mean, on that, we have all sorts of different requirements. So
Okay.
I think that Ben's referring to something more basic, making sure that when they measure their parts, that their variability within the measurement system itself is acceptable.
Correct.
Kind of a Gage R&R
Correct.
discussion, I think, one.
okay, sorry.
No, that's fine. I mean, we're here. Let me show you Gage R&R. Gage R&R is really required because one or two of the areas that we operate in require Gage R&R, and basically the question that's being asked with a Gage R&R is, how does the variation or the random error in my measurement system compare with the normal variability of my process? And if you think about it, if you've got, I mean, this is hard to do when you're facing into the camera, all your reflexes are backwards. If you've got this much variation in your measurement process and this much variation in your in the creation process, then the measurement variation is small compared with the natural process variation. And so life is good. I can resolve differences. And the example that I use a lot of times in our Six Sigma class is this. I've got a measurement system that will get me within a 1/16 of an inch 95% of the time. Gee, I really like my little measurement system. In fact, it's a tape measure and it rolls up and fits in my pocket. Now, do I have a good measurement system? Well, the answer is if I'm building houses where dimensional differences, if you take a tape measure and measure, you know, your living room at home or your bedroom, first of all, it's not square, and second, the dimensions of opposite walls are not the same, and very often they're off by an inch or more. So being able to resolve a 1/16 of an inch is plenty good. If I try to use that same measurement system to measure ball bearings, I'm going to fail because the variation in ball bearings is measured in 10,000ths of an inch. Okay, so Gage R&R compares your measurement system to your process and says which one has the most variation. Gage R&R is a fairly recent innovation, and it came out of the automotive industry. And there are two problems with Gage R&R. Believe me, I don't get horribly upset over these things because I'd much rather have a Gage R&R than have nothing. But there are two problems with it. Number one, the Gage R&R has a mathematical error at its heart. There's a math operation that it does that is not permissible. And I don't get horribly upset over that because it really does lead you in the right direction, even though it does an impossible math function. So the other thing that's wrong with it is that the traditional criteria of how low a Gage R&R can be, or how high it can be before it's a problem, leads you to spend money on better measurement systems than you really need. When they invented Gage R&R, somebody was not thinking right, because there's a real error there, and it drives you to have a better measurement system than you need. And that's not all bad. I'd much rather have one that's better than I need than one that's worse than I need. There is another tool that we like better. It's called intra-class correlation coefficient, or ICC. And that actually traces its heritage back to one of the greatest statisticians of the 20th century, and that's Ronald Fisher. And so it's well grounded. It doesn't have a mathematical error at its heart. It's less used than Gage RR. But I'm going to show you a third type of gauge investigation that I've decided really is a lot better than those two. It doesn't give you quite as much information, but it's not as complicated, and it gives you all the information that you need. And Don Wheeler, you'll hear me talk a lot about him, is the guru of this kind of stuff, and he introduced me to it, and I really love it. Let's get over here. All you do, Fred, this may be new to you. All you do is you have a standard in your area, and so if you're measuring 100 millimeter parts, you have a standard that's about 100 millimeters, and all you do is you go by about once a day and you measure that, and you just put it in an NMR chart. And if you know how to interpret it, you've got both your calibration and your variation in one simple tool that's intuitive and everybody can understand. So what I look for is, does my center line here line up with my expected value, the one that I know that object to be? And I would look at that and I would say, okay, this subgroup, this group of workers here, their calibration looks a little off to me. All right, their mean here is below. And the other thing that you can extract from this is, down here you've got your standard deviation of your process, and 68% of that is your effective resolution of your measurement tool. So here, in one very easy to understand graphic, you've got both calibration and variation. And the next version of QuikSigma that we bring out, we will keep ICC and we'll keep Gage RR, but the thing that we will recommend to our green belts, because it's effective and it's easy and everybody understands it after just a brief explanation, is what's called a gauge consistency study. And if you...
You're going to have to spend more time, because the NMR chart naturally includes the measurement variation and the process variation, and I don't know how to delineate which is causing my variation in the chart.
Oh, okay, good question. Let me go back, because what we do is we're not measuring stuff out of our process. What we've got is we've got a standard, like a gauge block. Okay, and so, or a thermometer, and we've got an ice and water bath, and you know, once a day we go check that standard temperature and record it on the NMR chart. So it's not there is no there's no process variation. Yeah, but because you can come down here and take 68% of the standard deviation, that gives you your effective resolution.
I got it.
Which is the smallest difference that you can discern. So
that was the piece I was missing. Thank you.
So I like this, and I'm going to start. It's going to get incorporated in our product. I like it because it's simple, and it gives you the information that you usually need, and it doesn't have big mistakes in its core like Gage RR does. That was a good question. Warren or Gene, any other questions? No?
I like what you're presenting here. Thanks.
Okay. All right. Now, the next thing that we have to ascertain is our process stable and predictable. So I'm going over here to a different data set, and I'll just click off. I tend to use all 4 of these rules just routinely. And I look at that, and I have, I know Fred's a little bit familiar with NMR charts. I suppose this is familiar, Gene, to you and Warren, to you as well?
Not to me. I'm not familiar with this at all.
Okay. Well, this, Warren, let me set the stage for you. Of all the tools, the mathematically oriented tools that you will ever use in your line of work, this is probably the most useful and also one of the simplest. Okay? So let me just describe to you how it works, and maybe I'll get you in one of my classes later on and we'll go into some more detail. But this is just simply my data in the order that it was created. So this is stuff as it fell off of my production line, or samples as I took them. And the center line, the green center line here, is just the mean of all the data.
Understand.
All right. Now I've got 2 red limits here that set the natural variation of my process. And if I get a point that is outside the limit, then what I know is that my process is very likely not stable and predictable.
Right.
Okay?
Got it.
Because then there's been some real change. Now, I have, so I've got this rule, 1 point outside the 3 sigma limits, and then I've got these other rules that help me. And if I violate any of those, and there are a bunch more, but these are the ones that work the best. If I have a data point that breaks a rule, then it'll put a little red number by it and say this is not stable and predictable. Okay? So if I look at data like this, I would expect this in a package of information from my supplier. And because I want him, the second thing on my list after I've got my measurement system working right, the next thing on my list is my process stable and predictable. Can I be reasonably assured that tomorrow I can do this process like I did it today and yesterday? And that's a big criterion. And if you know how to do NMR charts, then an absence of rule violations indicates to us that the process is stable and predictable. And that's a good thing. So this is the next thing you want to look at. Okay, so let's just take a look at something that's unstable. This is what starts to happen when the process is not stable and predictable. I start to get rule violations. See, I broke rule 3 several times and rule 2 a few times, and then I'm back down here breaking rules. And we just call this, because it's red numbers, we say you're getting fireworks. This is not a stable and predictable process, and if you see an NMR chart like this, you should say to your supplier, your process is not stable and predictable. Your output can go to 0 tomorrow, and you will have no clue why. So, good NMR chart, or excuse me, good NMR chart, bad NMR chart. Simple as that. You got a bunch of, now you will occasionally get out of limit conditions just by random chance, a few times per 1,000. But almost always when you start to get fireworks, something has changed in the process. And in fact, Walter Shewart, when he invented these charts, invented them because he had so many, he worked for Bell Labs and he had so many processes he didn't know what to do. And so he invented these charts so that the processes could tell him where he needed to go spend his time to fix things and investigate what was going on. So an INMR chart, if you're not familiar, oh, I should have told you, Warren, the top chart here is the individual data. The bottom chart is what we call the moving range. And you notice I've got one less point down here. This point right here is the difference between these two. And this one is the difference between these two. And so we call this we call it the moving range chart. Yeah. And you can get violations down here. And if you've got violations down here, those are as unpleasant as violations up here. Now there's more to it than that, and we like to take about an hour and a half to develop it. If you want to go to our web page, QuikSigmaLive.com, there's a tab there for videos, and there are recordings of past classes. You can go into those, and for not very much, you can look at recordings of past classes if you want to expand and know. There's a lot to know about INMR charts. They're so simple, and right at this point, Warren, even though you're saying it's your first introduction, I'm confident that if you looked at one now, you could interpret it and tell me what to do. They're just that easy. So now we've yeah, Lestelle has popped up the link for you. Thank you. That's in the chat box. Right. So the next thing on our list is we had to show that our process is capable, and so I've got a little chart here. This is the stable and predictable data, but now I've done something mysterious to it. What I've done is I've added spec limits here. Okay, that's all I have to do. And here I've got a distribution that shows the distribution of my data, and then I've got these normal curves drawn over it, and you notice I've got two specifications. I put up two. You don't need to, you can just do one. But you look at this, and the tails of the normal curve do not come anywhere close to the spec limits. And what that says is we're not normally going to make defective parts. And this is called a process capability study. And you're only allowed to do this for incoming parts anyway. You're only allowed to do this if the process is stable and predictable. That comes first. Then comes the capability study. And so I can look down here, and I'm getting these four indices, PPK and CPK, P sub P and C sub P. You have to understand how those all work together. People make the mistake of asking for CPK. What you want is PPK. In fact, I've got a little video on YouTube. If you look for QuikSigma and CPK, you'll see this little 5-minute video that explains the perils of doing that. But you want PPK, and just here's some rough rules. You want your supplier to be giving you the same answer over and over again. Yeah, my PPK is this much, and it's all pretty consistent and over a long period of time. The rule is, if your PPK is 1, that's just kind of the edge of respectability. And you wouldn't be real happy about a lot with a PPK of 1. That means you're going to have, if your process is normally distributed, and sometimes they are, that means that you're going to have 0.3% bad. Fred, is 0.3% bad okay?
You're venturing into where I'd like to kind of steer your discussion if I could.
Go ahead.
Since this is ATK Day, let me make a request.
Sure.
If we were in Lake City receiving thousands of brass cups a day, not thousands, I take it back, millions of brass cups a day, then this sort of an INMR chart is very easily visible for us to say, yep, that makes sense, let's go do it. We are procuring things for rocket motors that we build 12 in a year, or 2 in a year, or 1 in every 3 years. They're very individual pieces. How would you suggest that this would apply for those sorts of operations?
I'm so glad that you asked, Fred. There is an answer for that. And it's called short-term SPC. And there is a way to do it. The short answer is this. Take a simple example. You've got a lathe, and you're turning, 4 or 5 aluminum rods for this application, and then you've got another one that's got a different dimension, and another one that's got a different dimension. So you make 5 of this one, and 6 of this, and 9 of the next one. And how do you combine and manage that data? And the answer is that you subtract the target from all of them. And what that does is it does an INMR chart not on the parts, but on the lathe that is producing them. And then you can go right ahead and do your capability study just as well. So yeah, there is a way of handling that. It's called ShortRun SPC.
Yeah, we need to spend more time then, because you're not all the way into the level that we need you to be in your thinking yet either.
Okay.
We may have a supplier who runs 2 parts for us.
Okay.
And we don't order those parts again from that supplier, any parts from that supplier, for 3 years.
Okay.
And then we're going to order 2 more.
Okay.
So there's keep going with your train of thought, but be thinking about very, very low production volumes and what you would suggest.
Yeah, that gets harder. Yeah, go ahead, Gene.
Well, and Fred actually said exactly what I was thinking as well. Another challenge we have is we have some custom parts, but as we try and go to more military or industry government specification parts that we buy off the shelf that aren't manufactured to our specifications, again, that adds another layer of challenge.
Yep. Indeed.
And working with suppliers where our spend is small in comparison to their other customers. So a couple of challenges, kind of like Fred said, that I'm throwing out for you to consider as we go forward in our discussion.
Yeah, that's a splendid opportunity. Those are difficult problems. Okay, there are some solutions. There are some things that do not have a mathematical solution, and you end up using some of the other tools. And that's completely okay. That happens, and that can be handled. Maybe not quite as gracefully as this. Okay.
Okay, very good. I don't mean to get you off
No, that's
track,
fine. What you want to know about is at least as important as what I brought to the meeting. So I'm happy to answer questions. Okay, now the next thing that you have to have is that if you leave processes to their own devices, they will wander off into la-la land. And so you've got to have some way of knowing that your process does not wander. Let me give you an example. We did some work for a mining operation up in Idaho. And before we got there, they decided to save a little money by, they had some people, what they were doing is they were digging up phosphate rock, and then they would crush it up in a ball mill, and then they would pour sulfuric acid over it, and then what you get out of that is phosphoric acid, which is a chemical feedstock, and it's also a feedstock for a lot of fertilizers. Pretty cheap stuff. But they had some guys that were running the mill ponds, or where they would collect water, and they said to those guys, look, we're going to let the guys that maintain the ball mills go, and you're going to take over that responsibility, and that'll save us some money, because neither one of you are fully busy. Well, the pond guys didn't think that the ball mill was that important. It wasn't that central to them. And so a ball mill is just a great big cement mixer with cannonballs in it. And those cannonballs come around and they fall and they smash the ore to powder. They didn't change the cannonballs. And those cannonballs are continually being worn down by the rock they're smashing. So one of the green belts in the middle of his project decided to do an NMR chart on the conversion of ore to useful product, and the percentage was just drifting down over time. It had only gone down about 0.75%, but you could easily see it on an NMR chart. It had cost them $750,000 to save themselves probably $50,000 in personnel costs. And nobody had noticed. They had no control plan in place. They weren't looking at their key variables. So having some kind of a control plan in place is important, because those key things will drift over time, and you want to make sure that they don't. So a control plan is just very simple. You have to find out the critical variables. So that's what we've got here. And I just made some stuff up. What improvements did we put in place? And then we have to put up a tripwire that says, if you trip this wire, then I'm going to pay attention. So what am I going to do? I can weekly do a capability study if I've got a poka-yoke that's successful. And Fred will help you pronounce that correctly, won't you, Fred?
You bet.
If I say poka-yoke, will you get after me?
No, I've gotten numb to it.
I don't know if you guys know Fred that well, but Fred spent some time in Japan and is fluent, and he would like us to pronounce it poka-yoke, which is I think how it's said.
Actually, poka-yokeru. That's okay.
But say it again, Fred.
Poka-yokeru.
I can't do that.
That's impressive. I don't know that I can either.
Don't worry about it. It's okay.
Poka-yokeru.
Call it mistake proofing, and then we'll be good.
Fred, I've got to sit down with you. It may cost me lunch, but I've got to learn to say that. I mean, my students will be so impressed. And so you set up a tripwire, something that you're going to do that's going to catch it if you've got a mistake, and then you decide in advance how you're going to respond to that. And that's a control plan. So those are the four things that classically we look at. Measurement system, and that applies in your case. Stable and predictable. There's another way to get there in the special case where you're building a rocket motor that you only build every couple of years. There are some ways to get at that. The quick and dirty way is what I described, and if that's not good enough, then you're forced to yet another approach to it. And a control plan. Control plan, your client can have that, and we can show you how to set up some other things that they need to have if it's all the time these little tiny quantities. Big things bought rarely.
So let me ask a quick question.
Sure.
So a lot of your clients who are dealing with their supply chain make these things contract deliverables?
Yes.
So what we, if I'm understanding right, then what we would do is make each of the critical variables for which we would normally do receiving inspection for confirmation, part of the deliverable requirement that they have an evidenced control plan based on statistical studies.
Based on statistical studies or based on some of the other tools. What you have to do then, there are all sorts of things that you can resort to get some of the estimates that you need. But basically, you want assurance that, number one, their measurement system is telling something close enough to the truth. Number two, you want to make sure that their processes are under control and that they're repeatable and that they produce good parts, and you want them to give you a control plan that shows you that they have investigated and they have done that, and you're doing things like FMEA and so forth. But yeah, frequently these are contract deliverable items. This documentation will come with the parts.
Let me ask you another question. To what extent do your clients participate with their suppliers in the initial assessment of these items?
So now, are you talking about inspection, or are you talking about putting up the system, or what?
I'm sorry, I just had somebody walk into my office, so I was a little distracted. Well, to what extent, for instance, a control plan or measurement studies to ensure that their measurement system is under control and their process is under control, to what extent do many of your clients participate with their suppliers in those activities? Or are you seeing that many of your clients will have these as deliverables as part of the contract, and they might review the end product, but they're not a participant?
I'm going to fudge the.
Was I clear there?
Yeah. I'm going to fudge the answer a little bit and say that the wholesome ones get very involved. It's just a really good idea to kind of try to dissolve the membrane between the two companies. This should be a collaborative effort. That is, in my view, the healthy way to do it.
And recipe for probably continued success in the future.